Yep. So we are recording. I think everything's. All right, so I'm going to share the screen. I don't have to do the course participation anymore. And I'll be looking in a weird way. It's just that I never teach in here. This is my first time actually. All right, so I graded one of your homework assignments. I started grading that, and I'll be grading the next one soon. As far as the content, take a look. So as you can see, this we've covered the machine learning pipeline, matrices and vectors, KNN, and we started performance metrics, right? So I started going over a tool called Weka, and I will be emphasizing today the lecture basically of it. So we've used the tool now, and so you guys will see the kind of a little bit of the background of the topic of performance metrics. So we'll go over that. You do have a homework assignment that's due by the 5th. But yeah, so that the plan today is just to go over these. So if you remember, we saw performance metrics in Weka, right, on Wednesday. Okay, and we went over loading a data set like Iris, MNIST, and then we were able to do some training with some machine learning algorithms, and then we were able to look at the performance of it, right, the classification, precision, recall, etc. Okay, so that's the plan. All right, so we saw that. We also did a little bit of feature ranking. Feature ranking is kind of a different topic. Today, I'm just going to focus on those performance metrics. So the accuracy, F1 measure, precision, recall, and the confusion matrix, and see how they're all kind of related and where all of them are coming from. Then I have this nice set of slides. I'll go through that. Let me just check the Zoom again in case. Nope, nobody came through this, so okay. All right, so let's get started then. I'm going to click on the slides here. Also, just let me look at the calendar real quick. Okay, so if we look at the course, you'll see we are basically here, right? And going over performance metrics. As you can see this, we're kind of wrapping up that topic and then moving into a longer topic called singular value decomposition, which will be the topic starting Wednesday. But it's a very interesting topic. We'll look at something called the recommender systems. So like Netflix and Amazon, basically, they recommend products to you. And so we'll see how that can be done, and that can be done in several ways. Sometimes referred to as collaborative machine learning. All right, so let's go back to the slides. I'm going to download. So I'm going to download the slide. Okay, so performance metrics, you kind of I've already motivated what it is, right? So you guys know it's the way that we measure how good an algorithm is, right? So you guys saw 85% accuracy, 80% accuracy, etc. So, you know, we'll basically want to understand how these things work. So performance metrics, whenever we have a machine learning algorithm, we have data, right? So machine learning is all about learning, you know, training a model. We have a model, some architecture, but for that architecture, we have to learn the specific weights that connect everything in that architecture, right? And then once we've learned those weights, we can learn an infinite amount of weights, sets of weights, right? And so as we're doing this, we need to evaluate which set of weights is the best one, right? So basically, what are the performance metrics there? So determine how well a model performs on the data. Now, we usually then divide the data into several sets. So the idea is you have a problem and you're going to go out and get the data from some source. Imagine a lot of text data, for instance, right? You go and you crawl Reddit and you crawl a whole bunch of different forums. And so now you have all this text data. And so what do you need to train your model with it, but at the same time, you need to save some subsets of that data to be used for evaluation, right? Now, the model should never see the evaluation sets, okay? So it should never happen. So basically here you can see we divide it usually into train and at least into train and test. But some people do train, validation, and test. And basically what that means is we build a model, train, then we kind of tweak it on another set. We kind of assume the model already learned a little bit, but we now apply another data set to kind of validate it a little bit more, fine tune it, if you will. And then finally, once we think the model is in pretty good shape, then we test it basically on the test set. So this is not a specific rule. As you saw in Weka, we actually were able to change this if we wanted to, right? So we did like 70%, 66%, whatever you want it to be. Somewhere along the lines of like 80 to 20% should be fine. It really just depends on how big your data set is. That's really. But obviously you want your model to learn. Now, another thing about how we split the data set is we do it in a random fashion, right? So we want to randomize all the samples and then take the data like that, because remember, there could be bias. There could be bias in everything that we do. When a person is annotating or preparing the data set for the first time, they may have a bias that they're throwing in, right? And so then you have another, let's say that you had a person that did the train set, and then you had another person that did the validation, and then another person that did the test set. Each one of these people could have added some kind of a bias in there. And so, some subjectivity. And so that's why it's a good idea to grab a little bit of every single one. And that's why you randomize the data, basically. And you should always do that. Another approach is the tenfold cross-validation. If you remember, I didn't really use this one, if I remember, on Weka, but it was there. It was one of the options there, tenfold cross-validation. And this is actually, you guys can do it on your own. It's not like, I need to do anything special. But basically, this is a nice approach, because instead of just evaluating your data set once, you're going to evaluate it 10 times. That's why it's called tenfold cross-validation. So instead of randomizing the data, like in this approach, and taking 70% of it for training, 30% for testing once, what you do is you're going to take your whole data set, divide it into 10 bins, okay? That's where the 10 things come in. So you divide it into 10 bins, and then you're going to iterate through it 10 times. So the first iteration basically is this one, right? So you hold that one out as a test set and you train on the other 9. Then the next iteration, what do you do now? Now you hold on to this one, and then you train on this one and all the other 9, okay? So that's basically the idea here. Okay. Right. So, and then the third iteration, you would hold out this one, right? So you hold out on that one for training, and then all the other ones are going to be for testing. Okay, so you can see how that's kind of nice, because every time you're evaluating on a different set, every time you're randomizing the data, and every time you're training the model on a different set. So that's, you know, sometimes you could think of it as doing an epoch. An epoch is usually doing a pass through the data once. So you go through all the data once, and actually machine learning algorithms do this a lot, which is, you know, it's a concept that took me a while to actually realize, right? That you don't just have to look at the data one time. You know, I kind of thought it was like cheating. You know, I'm like, no, you look at it once. Why would you look at it 50 times the same thing? That's got to be cheating, right? But actually, it's just the nature of machine learning. You might have a data set of 1 million tweets or whatever it is that you learn, images. One epoch is one time. Look at everything one time. Second epoch, look at everything another time. But every time, the key thing there is that you're not looking at the data in the same way. You're randomizing the data. With, you know, some samples for training, some samples for testing. Anyway, this is an important concept, tenfold cross-validation, because, you know, which one of these, if now for both of these, you're going to get, you know, all the metrics, right? Precision, recall, F1 measure, precision, recall, F1 measure. But which one of these two approaches would you say is the most reliable for evaluating your model? Yeah. Why? Right. And with different views of the data, right? So at the end of the day, it's like you take an average of all the scores that you're getting, right? So every iteration you're getting a score, and at the end you're going to basically take the overall score. Yeah, so definitely this is the more reliable one, the more reliable approach. So tenfold cross-validation is a way of splitting our data. Now the metrics, as we saw in the WECA motivation, basically, we have accuracy, precision, recall, F measure, the confusion matrix, and there's something else called the ROC curve. We will mainly focus on these today, okay? And as you will see, all of these derive basically from the confusion matrix. Okay, so all of these derive from the confusion matrix. So we'll first just look at kind of the equations and how it works. And they're very simple equations. And then after that, we will look at an example, right, where we can understand. So basically what I would say is, if your data set is balanced, accuracy is so if your data, let me see. So if your data set is balanced, accuracy is reliable. So for instance, that means that when I say a balanced data set, I mean, oops. Yeah, when I say a data set is balanced, I mean that there's, you know, the classes, right? They're equivalent. We saw this with the IRIS data set with MNIST. We had basically equal amounts of samples for each class. But if we have a highly imbalanced data set, then at that point, accuracy becomes less reliable, okay? So that's an important issue. So for instance, think about the following example. Let's say that you're doing fraud detection in a bank, right? And you look at all the transactions in the bank that have taken place. How many of those transactions would you say are related to fraud? Out of all the transactions in the bank, how many would you say are related to fraud? Sure, okay, but how? So that could be, you know, 49 to 51%. But give me a more, even less probably, right? Yeah. I mean, otherwise, a lot of people are trying to cheat the bank, right? So think about that, right? So really not that many people are committing fraud out of everyone else that's just using regular banking out of all the transactions. So really 1%, 2%. So imagine if you're building a system that, let's say 2%, just if you're building a system for fraud detection, you end up with, you know, 98% of your samples, yeah, are good, you know, one class, class 1, and then 2% of your samples are class 2. You see that? That's a highly imbalanced data set. You actually, in fact, don't have that many examples of class 2. You have a lot of examples of class 1. This is a problem in machine learning. It's a big problem. And when you have something like this, accuracy becomes a lot less reliable, okay? And so you have to really start to look at the other ones like precision, recall, and F-measure, okay? And so that's what we're going to discuss today, kind of what they are, and you know, get an intuition for this. So you know, the classic example of this is like you know, finding something like fraud, right? You don't want to miss it. So what do? Do you either, are you very precise and you miss some fraud cases, or are you, you know, cast a wide net, right, and grab a lot of people, but not everyone would be involved. Everyone that's even slightly suspicious, right? That's precision and recall, one or the other. Okay, so either very precise and you miss some, or super wide net, but you have a lot of false people there. All right, so false, you know, people that are not committing fraud are going to get caught in the net. So performance classifiers. We will see later in the semester how to do this in the code. Obviously, you know, we are programming in Python. I introduced the performance metrics on to be used on Weka, but we will also need to be able to evaluate these in Python. So we will be using a library called sklearn. I don't know if I've introduced it yet, but sklearn, you know, will be the library to use. It's got some it's got all the metrics basically. So it's the same logic, it's the same theory, same metrics even. It's just, you know, we'll be able to access it through Python. And these are actually the function calls in sklearn. So in sklearn, right, these are the function calls: accuracy score, recall score, F1 measure, precision score, and the confusion matrix. So let's take a look at accuracy here. So this is actually a confusion matrix, the little table that you see there. So the idea is you tabulate, depending on the number of classes, how many, you know, you do something like, you know, what is the true class 1, true class 0, right? So you can see that here. And then on the other end, you have the predicted, so that you can compare and say, okay, out of 100 that were true, only 70 were predicted as, you know, this class. Right, so that's the idea. So usually then we're going to refer to each place where these meet, where these categories meet, as A, B, C, D. Okay, so then that way we can use this little table to figure out what the accuracy is. So here the accuracy is going to be, you know, because here this is going to represent the quantities of samples that fall into these categories. So for instance, if class is really 1 and the model predicts 1, then that's A, right? If class is really 1, but the model predicted 0, then that's B. You see that? That's basically what it is. Then when we have, if the class is 0 and the model predicted 1, that's C. It's a mistake, right? And then if we look over here, if the class is 0 and the predicted is 0, okay, that's a match, that's D. All right, so given this table, we can calculate accuracy then as, you know, out of all the samples, so that in the denominator we have A, B, C, D, and in the numerator, we will just have okay, so in the numerator, it's kind of difficult to write on here. So in the numerator, we will have A and we will have D, because those are where the class was 0 and the model predicted 0, or the class was 1 and the model predicted 1. So they are accurate, all right? So then the numerator is A plus T divided by this. That's your accuracy. Does that make sense, guys? All right. So that should be pretty straightforward. Now we look at the other ones of precision and recall and what they mean. So in precision, look over here. So what is the precision? So in the denominator, we're going to look at A and C. Right? And what is A and C? Well, if we think about it, out of the true, so we look at the true here, out of the predicted, right? We have A and C. So out of all the predicted that we have, right, how many of those were actually true? Does this make sense? So it's the model is going to give us something, right? We care about the model, we built the model. So the model tells us, okay, out of the predicted, I predicted these, but how many of those actually were useful? Okay. And so that's kind of the example of casting a wide net, right? So there's a wide net and then, but actually how many were correct? So that's precision. Oops. Right. And then recall, if we look at recall, then it's going to be A and B. So out of the actual ones, how many of those did the model predict? Right? And that's going to be your recall. So A plus B, out of the true, right? How many did the model actually predict as the class? And that's the recall. Okay, finding the actual thing that's useful. All right, so these are the definitions of these. The F measure is what is called a harmonic mean. So it's a mean that actually gives weights to precision and recall. We'll see how this works a little bit better in an example that I have here in the slides. But it basically, for now, let's just think of it. If you notice in the formula, it combines precision and recall. Okay, so in a sense, it's a good way. If you can only look at one metric, you usually look at the F1 measure. Okay, because that's the metric that will combine everything in. Okay, so you would have to calculate these first, calculate the precision and the recall, and then figure out the F measure. Questions about this? Any questions? All right, and here the confusion matrix is actually a very useful tool. What the way that it works is as follows. Imagine we have, this is the iris data set, right? So this is the iris data set that we looked at. Remember, it's got 150 samples, but we probably trained with 100, and now we're evaluating on 50. So this should be out of 50 samples, this confusion matrix. This is the validation or testing, right? And so here we have the three classes, acetosa, versicolor, virginica. That's A, B, C. And then over here is the same thing. So these are actually exactly like these tables over here, only this one has three classes. So what we look at is that for class A, it classified 49 samples as A and nothing else as B or C. So that means it's pretty accurate here, because what we want is that we want high values on the diagonal and no values elsewhere, right? We can see that for class B, we have some misclassifications, right? So of the ones that are B, it correctly classified 46, but it misclassified 4 samples as C, okay? And then in the last one we have here for class C, it classified 46 again correctly, and it misclassified 4 as B. All right, so you can see that there. You can see that there. The confusion matrix is useful because it provides information about misclassifications. It's actually a really very useful tool that whenever possible you should take a look at. It also allows you to figure out you know, where the problem might be, and then you know, how to go about fixing your model. You know, you might identify, well, here what I would conclude is, it's really good at predicting A, what's going on with B and C, right? That's really where I would focus my attention, because the misclassifications are happening there. All right, so round two. Now let's take a look at this, but with an example. Okay, so hopefully this will become more intuitive. This is, you know, you guys like cybersecurity, so this is kind of that area. All right, so so let's think of the, you know, airports and trying to detect you know, terrorism or something. So would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy? You know, what if they came to your office and they're like, hey, I'm going to sell this to you, 99% accuracy? Would you buy it? Well, you might be impressed at first, right? Because you, well, 99% accuracy, that's pretty good, I think, right? But actually, if you really look at it, you will realize that accuracy is a really bad indicator here. And that's why you have to look at precision recall and F1 measure. So here's the model. Simply label every single person flying from a US airport as not a terrorist. Boom, 99% accuracy right there, right? Because there are 800 million average passengers on US flights per year. There were only 19 confirmed terrorists that boarded US flights between 2000 and 2017. So look at those numbers. You're talking about astronomically different numbers, right? You know, a ratio of 19 to 800 million, right? So not very balanced, I would say. You know, this classifier has 800 million samples of one class, 19 of them. You see that? So that's very problematic. But it is true that this model, if you just label everyone as a not a terrorist, it achieves almost 100% accuracy. So it might sound impressive, but you know, you're not going to sell them all. So while this solution has nearly perfect accuracy, this problem is one in which accuracy is clearly not an adequate metric, okay? And that's why in machine learning, we need to have these other metrics of precision recall and F1 measure. And you actually kind of want to look at all of them. You kind of want to look at all of them. All right, so, oops, sorry, I keep hitting that keyboard. All right, so the terrorist detection task is an imbalanced classification problem, right? Really imbalanced. Most of the problems like fraud detection, terrorist detection, a lot of problems actually are going to be very imbalanced, okay? So you really have to almost think differently, right? You have to think, you know, all right, what is my goal, you know, and then which is the metric that's appropriate for this? Is it a combination of metrics, etc.? Here we have two classes that we need to identify, terrorists and not terrorists, with one category representing the overwhelming majority of the data points. Another imbalanced classification problem occurs in disease detection when the rate of the disease in the public is very low. In both these cases, the positive case, disease or terrorist, is greatly outnumbered by the negative class. These types of problems are examples of the fairly common case in data science when accuracy is not a good measure of assessing model performance. All right. Now we will, during the semester, because we're using a lot of just like, you know, academic, you know, textbook data sets, there a lot of the time things are very balanced and, you know, accuracy is really good. And you might get into that habit of looking at accuracy first, but just be aware you really want to look at all of them. And that's why all the metrics will always be printed, right? So we'll never just rely on accuracy. You can rely on accuracy alone just when you really know what you're doing, right? Like, you know, okay, no, this data set is highly balanced and this is good. But in general, always try to get that confusion matrix and get as many metrics as you can. So intuitively, we know that finding all negative data points in the terrorist detection problem is not helpful. And instead, we should focus on identifying the positive cases. The metric our intuition tells us we should maximize is known in statistics as recall, or the ability of a model to find all the relevant cases within a data set. All right, so here's another way that you may have looked at this topic. Like if you've taken a statistics course, instead of A and B, you probably saw it as true positives, false positives, true negatives, right? So you may have seen that terminology. So we're gonna take a look at it. So you can see it's exactly the same thing we had before. I just changed the letters A, B, C, D to be true, positive, and so on. So here we have positive, negative, positive, negative. So obviously, if it's the actual is positive and predicted is positive, that's a true positive. If the negative is, if the actual is negative, the predictive is negative, that's a true negative. And of course, the other ones are going to be false positive and false negative. So in recall, for instance, for this problem, the precise definition of recall is the number of true positives. Okay, so the number of true positives, right? Maybe I'll start divided by the number of true positives plus the number of false negatives. So if you can see, it's exactly what we had done before, but now in the example. Okay, by the number of true positives plus the number of false negatives. True positives are data points classified as positive by the model that actually are positive, meaning they are correct. And false negatives are data points the model identifies as negative that actually are, in fact, positive. In the terrorism case, true positives are correctly identified terrorists, and false negatives would be terrorist individuals the model labels as not terrorists that actually were terrorists. Okay. So recall can be thought of as the model's ability to find all data points of interest in a data set. And you can see here in this equation, we have recall, true positives, divided by true positives plus false negatives. So it's terrorists correctly identified, divided by terrorists correctly identified, and terrorists incorrectly labeled as not terrorists. Okay, so that's the recall. Any questions? Making sense? Okay. And then, so how can we find all terrorists? In this case, let us predict everyone as a terrorist and problem solve. Recall will be high, right? But in the case of recall, when we increase the recall, we decrease precision. So it's a little balanced. So, keep that in mind, right? So very high recall results in very low precision. All right, so precision is defined as the number of true positives. It's the number of true positives divided by the number of true positives plus the number of false positives. So you can see it's, what we had said before. False positives are cases the model incorrectly labels as positive that are actually negative. Or in our example, individuals the model classified as terrorists that are not. Precision expresses the proportion of the data points our model says were relevant and actually were relevant. So here again, we have precision in terms of terrorists. So it's terrorists correctly identified divided by terrorists correctly identified plus individuals incorrectly labeled as terrorists. So notice the difference, right? So, before it was terrorists incorrectly labeled as not terrorists. Now it's individuals incorrectly labeled as terrorists. That's really the difference. Yeah, go ahead.
If precision increases, do any other stats decrease? Does recall decrease if precision increases?
That's what it just said, right? Precision, when one goes up, the other one can go. The other one can go down. So you want to find a balance. Okay. So, and this is kind of expressed here. So now we can see that our first model, which labeled that all individuals as not terrorists, wasn't very useful accuracy. Although it had near perfect accurate, had 0 precision and 0 recall because there were no true positives. Say we modify the model slightly and identify a single individual correctly as a terrorist. Now our precision will be 1, no false positives, but our recall will be very low. You see that? So it's like, I found this one and that's, but you know, you're missing out everyone else. And then you can see if we go to the other extreme and classify all passengers as terrorists, we will have a recall of 1. You know, we'll catch every terrorist. Sure. I mean, if you know, 800 million, right? But our precision will be very low and we'll detain many innocent individuals. So that's really the little balance. So keep that in mind. Precision and recall are like that. So in other words, as we increase precision, we decrease recall and vice versa. So you can see that this was Lenny's question. Okay, make sense? Making sense? All right. So this is the idea of why we need all these metrics. So the best recommendation when you do machine learning, especially here, we're just looking. Now, keep in mind, these are not the only metrics in machine learning, right? These are only the metrics for supervised learning. You know, we have also, it's like 30 other for, you know, in language generation and things like that. And of course, in linear regression, there's also different approaches to evaluate things. Okay. Now, combining precision and recall, in some situations, we might know that we want to maximize either recall or precision at the expense of the other metric. For example, in preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. So we want to find all patients who actually have cancer, and we can accept a low precision if the cost of the follow-up examination is not significant. Right? So it depends on the resource, but you don't want to miss, you know, a case. So you're gonna want that. However, in cases where we want to find an optimal blend, so if we want an optimal blend of both, well, somebody just came in. I wonder if some people got the room number wrong. So she is in. All right. So anyway, let's go back. So, however, in cases where we want, I guess I should ask you. You have a question? Yeah.
I was unsure if the class was online or on campus today.
We are on we you know, according to the university, we're back. So we are where are we? Anderson 250.
Okay, thank you.
But it's fine. You can stay on this if you want. And I'll post a video later. Okay?
Thank you.
Okay, what was I saying? Yeah, so we were talking about the F1 measure. So in cases where we want to find an optimal blend of precision and recall, we can combine the 2 metrics using what is called the F1 score. Now you can see the F1 score here. It's a combination of precision and recall. So the F1 score is defined as the harmonic mean of precision and recall, taking both metrics into account in the following equation. You can see that there. So you can see the equation there. So we use the harmonic mean instead of a simple average because it punishes extreme values. Okay, so A classifier with a precision of 1 and a recall of 0 has a simple average of 0.5, but an F1 score of 0. Do you guys see that? And that's the usefulness of it, right? So, you know, if you basically want to punish extreme values, as it says here. So if the precision is 1, but recall is 0, those are extreme values. So you punish it. If you take the average of 1 and 0 is 0.5, but the F1 score will return a 0. You see that? So it punishes it. The F1 score gives equal weight to both measures. And then there are other metrics for combining precision and recall, such as the geometric mean of precision and recall. But the F1 score is the most commonly used. Weights could also be adjusted to favor one or the other. If we want to create a balanced classification model with the optimal balance of recall and precision, then we try to maximize F1 score. And that's really why I said, if you can only use one metric for your model evaluation, then the F1 score is definitely the metric to use, okay? Because the F1 score, as you can see, it's because of all these reasons, it's a little bit better. Yes, if for a supervised learning problem, for a classification problem, which is like 3 classes, 2 classes, etc., that would be the most important F1 measure. F1 measure. If you, the way that I would say it is, it's not the most important necessarily, but if you can only look at one, that's the one to look at. You see that? Okay, so again, guys, for those of you coming in on Zoom, we are in Anderson 250 if you didn't know the room. You don't have to come to class today. Obviously, you can stay on Zoom, but I'm just letting you know, because I also had the room number wrong. All right. So performance evaluation of the performance of your classifiers is extremely important. The sklearn kit provides very good modules to address this issue. So we will be using actually sklearn. We will be using sklearn pretty much for the performance metrics. In particular, evaluation often involves, as you know, these metrics. And the best way to understand these metrics will be to look at the confusion matrix, which we will print out. So this is the code for this. I would recommend that you just have this function handy in your GitHub somewhere, so that whenever you're doing things, you can always just grab it easy. If you notice this function over here, the way it works, you can see here, print stats percentage trained test. It's just a function. You pass the algorithm name, just because whenever you're printing out results on several classifiers, you probably want to see the name of the classifier. And then you give it the Y test and the Y pred. So you give it the Y test set and the Y pred set, and then you're going to compare. Remember that what this means usually is, you know, you have, for instance, for iris, right? So you had 1, 1, 0, 1, and that's the Y test or the real. And then you have over here the Y pred, and Y pred is going to be the predicted value. So 1, 0, 0, 1. So as you can see here, we have one match, one match, one match, but this one is not a match. So if we just look at accuracy, it would be 3 out of 4, right? So that's pretty good, 75% accuracy. Okay, and so basically these are now, given this Y test and Y pred, we can calculate accuracy score. Notice that accuracy score takes Y test and Y pred, We can calculate the confusion matrix, which also takes y-test and y-pred. We can calculate the precision score, the recall score, and the F. And they're basically all the same. They take the same data. Questions? Pretty easy, right? Pretty straightforward. Okay, so we'll work on that function shortly, but just wanted to introduce that one because it's very handy actually. And then I've set this, so I'm not gonna talk about it. All right, so that's basically the slides. We're gonna switch over to Brightspace. All right, so we are here in Brightspace, as you can see, in performance metrics. Today, we're just evaluating this. So let's take a look. I have a Jupyter notebook here, and I have Python script. So let's take a look at that. I need my Mac for this. So as you can see here, so we're going to do this today, and these are just some examples of accuracy, etc. So for this, I'm going to need to move to the Jupyter notebook. So I'm going to start my Jupyter notebook here.
My machine is doing multi-processing scan still.
So let's say
Remember the multi-processing scan for the AI assignment?
multi-layer perceptron.
Yeah,
What did you call it?
multi-layer perception.
Multi-processing. Go ahead.
I have multi-layer processing.
It's still going.
Yeah, still going.
Yeah, remember what I said? Yeah. So again, remember I said this, right? The reason why I'm having you guys do that is because I want you to be traumatized by it. So that you choose never to do that again, and then understand the motivation as to why we have to move to slightly more complex frameworks, like something called TensorFlow, which is it's just a little bit harder to understand, but now you will be motivated because otherwise students just thought, no, I'm just going to use Blackout. I'm good. I don't need to learn this. Yeah, but it'll take you 32 hours to run. All right, so let me grab my Mac. So we'll go over. So these scripts, they're already posted online.
Like, are you in the server? You in the server? You want to run the server? Yeah. Just how you
All right, guys. So, so as I said, we're gonna do a couple of things. One of them is the function for the metrics. We're also going to introduce the sklearn library. So I believe I've installed this already. So let me do import sklearn. Am I sharing this? Okay, there it is. I'm sharing this now. Okay. So that's the sklearn library right there. If you don't have it, you'll have to install it, probably like pip install should do it. Yeah. You guys have this? All right, so the first thing we're going to look at is just how to get some data from sklearn. So let's do import numpy as np from sklearn import data sets from sklearn dot model selection import train test. Okay, so we're going to be using these functions. The data sets in sklearn will allow us to just get instead of having to read data from a CSV, we can just load it directly from the sklearn module. The train test split will allow us to split the data so that we can create something like the train set, the test set, the validation set, basically. So that's the idea. Okay, so here then, let's first of all load these in. Any questions?
Oh, no. I'm just having trouble getting text everywhere. So I'll just watch.
Okay. Just you know, Jupyter Notebook.
I have that on my home.
Oh.
It's in vain.
Yeah. It's all right. So now we're gonna get the data set. So the data set here is gonna be iris. It's just easy. So it's gonna be 150 samples. And it is 4 features. And it is 3 classes. Okay, so that's the iris data set. So we can just bring it in from sklearn because I already imported this module data sets, right? So I'm going to say data sets dot load iris. You know, I recommend that you go online and check out the data sets from sklearn module, and you can see all the different data sets that might be available there for you to play with. All right, once we have the data set, we're going to divide it into the X vector and the Y vector. So I'm going to do X, comma, Y, and I'm going to say iris dot data, comma, iris dot target. All right, so we got iris.data, iris.target, and that becomes the X and Y vectors, basically, that we're going to use. Now what we want to do is we can view this data if you want. So you can do print. For instance, if you print Y, it'll just give you a vector of 150 ones, twos, and threes, probably. Or 0, 1, and 2. See that? That's the labels, right? Those are the labels associated. So the first 50 are Setosa, then the next 50 ones are Virginica, and then Versicolor. if we want to look at the X data, we can do and there's the data set 4 columns per sample. You guys understand? We had talked about this before, correct? All right, so so this is our data set. I'm going to remove these. Okay, so now that we have our data here, the next thing we want to do is remember when we used Weka last week, we did the percentage split, right? We did, 70%, 30% split. This time around, we are going to do a split, but in Python here with sklearn. So I'm going to create now my X train and X test, comma, Y train and the Y test. Okay, so I have the 4, I'm going to have 4, 2 matrices, 2 vectors, 4 in all, 4 tensors, if you will, with the data. So the X train data with corresponding Y train, so that's the samples and labels, features and labels, and then X test with corresponding Y test. So again, features and labels. So to get these, we need to run a function. So in this case, we will run this function here, train test split. Okay, so I'm going to run train test split, and that's going to be train underscore test underscore split. Okay, this is going to take X, comma, Y, comma, and so it takes the original ones and it's going to generate these 4 new ones. Okay. We also want to specify the size of the test set. So we're going to say test set, test size. And we're going to say test size equal 0.3, for instance. So this is the equivalent of saying 70-30% split. Do you guys see that? So we're doing that. We just specify the tests and then it'll infer the train. Now we can also state a random. Remember that the data will be randomized. That is to say all the samples are going to be jumbled up. And then, but if we want to always get the same randomization, we can initialize it with a random state and just give it a number. That way we can control that. Okay, so now, did you guys have a KNN homework?
Yeah, we did.
You did?
Yeah. I love it.
Huh?
Yeah, no, it wasn't. I only came in with, one with the Weka homework. That's what it was.
No. Before that, didn't you have a KNN homework? I thought we went over the algebra. We didn't? It was never. Okay. All right. So then, yeah. Okay. So I'm going to combine. Yeah. Okay. I'll do it as part of this homework. All right. So let's run here. Okay. So the train test split should have been done now. If I do print Y test, you can see that it's much smaller now, and they're no longer in order, right? Which means it's been randomized and it's broken up into a smaller little subset, because now we have X train, X test, Y train, Y test. Okay, but we can see it here. So now, let's say that you are going to actually implement a full model. Remember, you did KNN and Weka. You know how to do it actually, right? You know how to do KNN and Weka. And so, and you also know how to do KNN and Weka with the iris data set because you have it. So you're going to actually repeat kind of the same thing here, but this time you're just going to do everything in Python. You can always compare your results from this to your results in Weka. As you know, it does really well, right? So, you know that when you do this homework, you also have to get really good results. Okay, so that's basically the idea. So what are you going to need for this? So we're going to need a couple of tools. We need the performance metric. So we're going to have to define that function. We're also just going to build an accuracy function from scratch, just to kind of take a look at it. And then you're going to have to bring in KNN. Okay, so what you're going to do then is here, remember, if we went over the KNN code, we'll go over that on Wednesday, but I just kind of want to motivate what I'm doing. So let's do from my KNN import my KNN, right? So what I'm doing here is, imagine that you have your own file, right? So you have your own file called my KNN. And so you're going to need to have that somewhere available to you, right? So for instance, so I'll have to check where I have that. I don't remember. But anyway, from my KNN, import my KNN. So you would bring in a my KNN file, right, where you have the definitions of KNN, and then you're going to import it. Okay, once you have it, then you would be able to use it, right? So you'd be able to use it down here. You already have the data set split. So you would do then something like K equal 5. And then you would do my ML KNN, my KNN, K equal K, right? So that's basically setting up an object, okay, or a function there. And now you can bring in your KNN code, okay? Then you're going to call the function my ML underscore KNN dot train. You're going to train on what? You're going to have to train on X underscore train, comma, Y train. Okay. And once you've trained the model on X train and Y train, then you're going to go ahead and predict. So you're going to say Y pred, and so you do my ML underscore KNN dot predict. And what do you predict on? Look at all the data sets that I have, right? What do you predict on? We're training on the train. So what do we predict on? Once you predict once the model is trained. Y test is the real set of labels. We are trying to come up with the predicted set of labels. Think about it, right? So this is the data set. The initial data set is this, X and Y. Then we split it into these four. That's it. These four are it. Huh? We're predicting a class. That's correct. We're predicting Y pred. Remember, X's are the features, Y's are the classes. So we get X train, X test, Y train, Y test. Okay. So if I have my KNN, I'm going to train. What do I train on? X train, Y train. Why? Because X train is the features, right? And Y train are the corresponding labels. You guys get it? Okay. So if I train on X train, Y train, what goes here? X test, exactly, X test. So let me go back to the whiteboard. So I have here, so I have X. Oops. Okay. So I have X and Y, right? This is 150 or 151. Do you see that? We are going to split, right? According to the function, it was 30%. So that means randomly, we're going to select 100 samples of this, right? 100 samples of these to go into X train, the other 50 to go into X test. So X train, X test. From here, we take 100, we take 50. Do you see that? And then the corresponding, it can't just be like any one, right? It's like if we grab this one, then we have to have the corresponding label for it, obviously, right? But the function takes care of that, and it creates Y train and Y test. Do you see that? So they correspond. Now, X train and Y train go together, right? And if and X test and Y test go together. Okay, one's got the labels of the other, the corresponding label. So the trick is, we do this because we're going to train using this. Okay. We're going to train using those two. And so that's going to be for the training, and the other one's for the testing. So if we go back to our code over here, you can see here, right? So I took X train and Y train. I'm going to train. And then given that the model's already trained, now I'm going to predict. I'm going to predict on X test. And that's going to give me Y pred. So what is then Y test? What is Y test for? Notice I've used X train, Y train, X test. I have not used Y test. That's what's in there. But Y pred also has predicted labels. What's it for? Yeah. to verify, right, for the evaluation. So the whole class today has been about performance evaluation. That's what is going to be done here. So when we do evaluations, we are going to do what? Y-pred compared to Y. You guys see that?
Yeah.
So that's what we're going to do. So let's do a simple, that should be a comment. Let's do a simple example. So we're going to create a function called accuracy or my accuracy, whatever you want to call it. Right? And this would give us a function that would give us an accuracy result. I'm going to comment this out for now. Okay, so I'm going to call that function and then I'm going to try to print the result. Okay, like that. So then we need to define this function. And so that's what I'm going to do here. I'll do define accuracy. Okay, so define accuracy. Keep in mind, this will take Y-pred, comma, Y-test, right? Because we need to compare the values that we have, the real ones, with the predicted one for the X test, okay, which are aligned. So here, to keep it simple right now, let's visualize it, right? So let's go ahead and visualize it here just by creating our own vectors. So let's say Y-pred is going to be equal to numpy array. And then we're just going to say 0, 0, 0, 1, 1, 1, 2, 2, 2, 1. So that's 10 values. Okay. Now let's do another one. This is going to be Y test NP array, but this one can be, that's a 1 and that's a 2. So basically there's a difference of what? 2, right? So should be 80% accurate. You guys see that? 2 are different. The other ones are exactly the same. So now I got the 2 vectors. Obviously, I'm just doing this so that we can visualize it completely. Just an example. So now in the function, we can specify accuracy value underscore value. NP dot sum. NP dot sum. So what we want to do is, actually, let's not do it. Let's think about how do we measure this? So we've got 2 vectors, right? We have 2 vectors of values. And we want to know, we can see it because we're smart, that 8 out of 10 are a match. But how do we do that with NumPy? So one nice little trick with NumPy is that you can just do something like y true equal, wait, y is y pred, sorry, y pred equal y test. So what we're doing there is basically we're looking at the two vectors. So if we go back to the whiteboard, so we've got two vectors there. We've got this other vector. Do you see that? So by doing an equal, we're basically going to take two vectors and return kind of a Boolean type of a vector that will say, yes, this is true, true, false, true. Do you see that? By doing that expression that I did before, it takes the values in the two vectors. So the first ones, they're the same, so true. Same, true. Not same, so false. Same, true. So 1, 1, 0. What's great about this is if I can now take a sum of these, right? So the sum of this will be what? 3. But there's 4 places. So 3, huh? Yeah, 3 divided by 4. So the length of this is 4, but the sum of these is 3. You see, so that's what I'm going to be doing here with NumPy. So very easily, then here, these two vectors will result in that basically. And now I can do, so we can actually print it, I guess. Okay, so we should be able to run this. You can see it there, right? So there they are, true, true, false, true, true. Okay, so now obviously what we want to do now is sum them. So I'm going to do np dot sum. It's going to treat the falses as zeros, the ones, the trues as 1. So if I have this np sum, then I can just, all I have to do is divide it. So I'm going to do divided by the length of what either one y test, they have the same dimensions, y test. So one gives me the number of places, the other one gives me the sum of truths. And that's accuracy. So now I'm just going to go ahead and return it. Return accuracy underscore value. Okay, now if we try this, this should give us 80% accuracy. And there it is. You see that 0.8? Does it make sense, guys? Yeah. That's basically it. Okay. So that's a simple accuracy. However, you won't really be doing it that way. Instead, we should actually have our metrics. So let's go to I'm just going to the slides. I want to copy that code. Here it is. Oh, this- oh, that's an image. So we need an efficient way. I'll have to look for it because I thought I had it here, but oh, here it is. Found it. Okay, so this is in. Okay. All right, so if we go to the GitHub, and then go to sklearn, and then several ML algorithms. Have the function in here. You can always just type it. Copy. All right, so now go back to the Jupyter notebook. All right, so there's the function. So the way it works is this is the function called print stats percentage train test, right? So just like we did before, but this is probably, we need to make this one work. I'm pretty sure there's a few little things that will make it break. But we would call the function and the function prints. So we just have to call it here. We specify the algorithm name. So for instance, KNN. See that? And then you would plug in Y test and Y pred. I always follow this convention of Y test, Y pred. That's like my own personal preference. But it's really what we did here, right? So we did it with a simple example just to kind of illustrate. However, it's not always practical to always implement your own. So we're just going to use the built-in functions here, accuracy score, precision score. These should be coming from sklearn over here. So we're going to have to do an import also of those functions. You see that? So that would be, I go back to that GitHub again. Here they are. So I'm just going to do that. And then I can go to the Jupyter notebook. Did I close that Jupyter notebook? Oh, it's on the Windows. All right. So now, let me share the make sure I'm sharing. Okay. So let's add a couple of libraries. Here they are: sklearn metrics, confusion matrix, precision score, recall, F1, and pandas. Right. Let's run that. Okay, perfect. Iris runs, split runs. Print this one. All right. And I know this one worked also. So now we've got this new function, right? It's going to take y-test, y-pred, so we can use the same data over here. But now instead of using our own accuracy and other metrics, we're going to use the built-in sklearn metrics. Everyone with me so far, guys? Are there any? Yeah. Are there any questions? No? Mm-hmm.
So you put for the np.some data slash len, is that like a learn? What does len do? Lang,
The length of the, remember we talked about it?
right.
Like there's 10 items, but only 8 of those were true.
Right. So it's 8.
No. The length is 10. There's 10 items. 8 of those are true, 2 are false. So the sum of true is 8 divided by the length. 8 divided by 10.80. All right, so we've got our function here, print stats percentage train test, y-test, y-pred, right? So now all we have to do is make sure that this works. So this function obviously needs some tweaking. So it's got to be in Python 3. So that'll work. Okay, so that should be correct. The algorithm name. So all of that should work. And let's just try the first one. All right, so if it works, accuracy should give us 80%, right? Okay, so let's run that. Okay, algorithms came in. Name accuracy score is not defined. I guess I forgot to include it here, huh? Comma. Let's try it. 0.80. You guys see that? We actually got 1 to work. Let's try the confusion matrix. Okay. And as you can see, what do you guys see? Is the confusion matrix, right? Just like we had in the previous examples, we have, remember, we're just using a data set of 10. You see that? So out of the 0, there was 1 misclassification. So 0, 1. We had, let's see. Take a look at the table. Oh, white test is actually the correct thing. So we had 2. 2s is 4. There are 4 1s and 2 0s, right? And we can see the, yeah, 4, 4, and 2, right? And apparently we had no misclassifications on 0, but we had misclassifications on 1 of 1 and of 2 of 1. Yeah. All right, so that's the confusion matrix. And now we can take a look at the other ones. Let's try precision. An error. Target is multi-class, but average equal binary. Please choose another average setting. One of, so I'll do average equal weighted. Okay. Average weighted. So. Did I have a typo or something? There it is. Look at the precision. And let's take a look at the other ones then. Recall and F measure. Let's just do 1. So this is probably the same error. Okay, let's try that again. There it is. There's the recall. And then let's do the last one, which is the F measure. Probably the same error. And there it is. Make sense? And that, so as you can see, we can also do what we did in Weka on last week, but now we can do it on Python as well. Okay, so this is a way. So whenever you're doing now your machine learning algorithms, right, you want to print out the metrics, precision, recall, F measure. All right, so on Wednesday, we will take this code But let me save it actually. This code, yeah, let me do that. Yeah. Some of it is, just not all of it. Yeah. Okay. Right, so it's got the, so we'll continue this. We have the performance metrics now, but on Wednesday, we will continue this part, tie it to the KNN that we did last week so that everything now works together. And then your goal should be to be able to process the iris data set with your own version of KNN and do all the evaluation, right? So we'll do that on Wednesday. That will be the plan. All right, so that's it for today. We'll stop here for today, and I'll see you Wednesday.